All right, so this lesson starts with long division, then we talk about synthetic division, but the new stuff is really the remainder theorem and the factor theorem. It's not brand new because you've known some of these concepts before, but let's review a little bit of long division. So we just went over the homework, which was long division, and so I'm not going to go through this whole thing step by step again, but everything is written out here. This should have been reviewed from last year. Remember that you're subtracting, so the only thing I would caution here is make sure you change your signs at that point right there. So this is actually negative 25 plus 18, right? You just got to be careful of that. Every time you do this subtraction, you got to really be careful of those signs. Okay? All right. So once you do that long division, what does that mean? Well, that means that x minus 3 is a factor of this whole polynomial as long as the remainder comes out to 0, right? If the remainder comes out to 0, then it's a factor. It goes in evenly, so it's a factor. So it's one way of factoring big, long polynomials because, you know, not everything's going to be a trinomial that we can just nicely factor. So division is going to help us factor bigger polynomials. This is what's left over when you pull this out. So you actually can write this polynomial as, you know, x minus 3 as one factor, and then 6x squared minus 7x minus 3 as what's left. Well, now we can keep factoring, right? We could take this, what's left, and we could factor that. So how does 6x squared minus 7x minus 3 factor? Well, everybody has their own method for doing this. I like the split method the best because it's just like factoring by grouping, which I think you guys all did last year anyway, right? Factoring by grouping. So the split method is just keep the first term, keep the last term, and then you're kind of uncombining like terms in the middle. But what you have to remember when you're doing this split method, you have to multiply A times C to get what you're trying to split this into. So 6 times negative 3 is a negative 18. And the middle term is negative 7, right? So you're thinking what multiplies to be negative 18 and adds to be negative 7. So what could we use? 2 and negative 9, right? So we have negative 9x plus 2x in the middle. That'll give us a negative 7x and multiply to be negative 18. And now we can kind of, you know, factor by grouping. Take out a greatest common factor, and that would be 3x squared. Sorry, 3x only, 3x. And that leaves us with 2x minus 3. And then in the second grouping, we can pull out a positive 1, and we're left with 2x minus 3. So factored form here is going to be 2x minus 3, which is the thing they had in common, and then 3x plus 1, which is these on the outside. So our final factored form of our original polynomial that we were dividing right here is this. This one down here has a remainder. When there's a remainder, you have to write the remainder as a fraction at the end. Just remember that if there's a remainder, then that means you haven't found a factor, right? If it doesn't go in evenly, it's not a factor. Now, something we want to make sure we point out here, if you remember from doing this last year, if there's missing terms, I mean missing meaning like not every single exponent is accounted for, then you have to use placeholders. So for this one here, right, if we do long division, 3x plus 2 on the outside, and then 9x to the third, there's no x squared term. I have to kind of put plus 0x squared. And then minus x plus 2. So you need to have that placeholder there. These answers come out to x plus 4 minus 20 over x squared minus 5x plus 6. This one had a remainder of a negative 20. And this one came out to 3x squared minus 2x plus 1. Okay? Now we can use long division to write the zeros of a polynomial, right? Just by dividing by whatever factor they're giving us. Let's do this one together, okay? X plus 6 goes into x to the third. Now we have to always look for, do we need placeholders? We don't actually need placeholders here. First term into first term. That's what you're thinking. First term into first term, right? So x goes into x to the third, x squared times. Then when you multiply, you're going to put your result here. Remember to distribute through the whole divisor here. So we get x to the third plus 6x squared. Now we need to subtract, but we're subtracting this whole thing. So make sure you're subtracting the 6x squared also. I like to change my signs and put it through like that. Whatever works for you. So I get x squared here. Now again, first term into first term. But we have to bring down the next term. Just one term, right? So x goes into x squared, x times. Distribute and put your result here. X squared plus 6x. Now we want to subtract. First terms should always cancel. Negative 2x. Now I got to bring down the minus 12. X plus 6 into, sorry, just first term, x into negative 2x goes minus 2 times. Then you're going to get negative 2x minus 12. Now, if that matches exactly, we know when we subtract, it's going to just end up with 0. So we found a factor. Well, they gave us a factor. So this polynomial can be rewritten as a product of this times this. So we have x plus 6 times x squared plus x minus 2 as a new way of writing f of x. But we could factor x squared plus x minus 2. We shouldn't need a method for this one, right? Because the leading coefficient is just 1. So we should be able to just factor it really easily, x and x. To get a negative 2, I would have to do a positive 2 minus 1 to get a positive 1 as my middle term. So what are the zeros? Negative 6, positive 1, and negative 2. Synthetic division sometimes is considered an easier way to do this process, right? You can divide, and you don't have to worry about all of the x's and everything until the end. When you do synthetic division, I set mine up a little bit differently than that. I usually do a whole bar across like that. If you are dividing, in this case, by x minus 3, you actually outside are putting the x value that would be the actual solution, right? So the actual solution, if the factor is x minus 3, the actual solution would be positive 3. So you're putting a positive 3 on the outside. And then these numbers that you put inside here are just the coefficients of your polynomial. You don't put the x squareds and everything. You still need placeholders, right? So it's really important that you still are thinking about placeholders. When you're done, you end up with the coefficients of your new quotient, okay? That thing that you end up with, that polynomial that you can write, is called the depressed polynomial. Okay? So you'll see that term sometimes. All right, so let's do a synthetic division here. So we're dividing by x minus 3 again. So what number do I put on the outside? Positive 3. And then inside, we're just going to copy these coefficients. Don't forget to look if we need placeholders. I got to the 5th, to the 4th, to the 3rd, to the 2nd, to the 1st, and a constant. So I don't need placeholders here. But you should always look and see. Okay? So don't forget to keep your signs of your coefficients, because that's important. Okay, running out of space here. Okay, where my constant goes, I like to put a little nook here because I know that's going to be my remainder. So I put that at the beginning, then I know I'm keeping track. Now, here's the process. And it's written out on the page before the process, but the first thing you want to do is just bring down that first term. You don't need to do anything to it, just bring it down. And then the process begins. Whatever you're dividing by times the 2 now, because that's what we brought down. 3 times 2, we put 6, we put it here. And then you're just going to add. Negative 4 plus 6 is positive 2. Now we multiply again. 3 times 2, we get 6. Then we add. Then we multiply again. 3 times 3, we get 9. And then we add. And then we multiply again. 3 times 3, and then we add. And that didn't come out. Why did that not come out? Oh yeah, because this one has a remainder. Good. We wanted it to not come out. Okay. And we add, and it comes out with a remainder. So our answer here, we write this depressed polynomial with its new variables. This was an x to the 5th term, right? So now the depressed polynomial is going to be one less. So this is going to be 2x to the 4th plus 2x to the 3rd plus 3x squared plus 3x plus 4, and then the remainder, plus 4 over what we were dividing by, x minus 3. Okay, I'm going to skip B. B has a, we're dividing by 4x plus 1. What would be the actual solution to that? Negative 1/4. So you actually have to divide everything through by 4 here. And it makes it like a little bit tricky. In the interest of time, I'm going to go back to that, okay? Because our real purpose here is to use synthetic division to be able to factor polynomials. All right, so let's do this one, right? They're telling you x equals 4 is a 0 of this polynomial. Be careful here the way this is worded. They're not saying divide by x plus 4 or whatever, right? They're telling you that the 0 is 4. So when we do our synthetic division, actual 4 is going to go on the outside of our synthetic division. We're not changing the sign for this one because it doesn't say divide by x minus 4 or x plus 4. It tells you the 0 is 4. So we're actually dividing by 4. X to the third has a coefficient of 1. We don't need placeholders here. All right, guys, so for this one, your synthetic division should have looked like this. Zero remainder. So this is the depressed polynomial. We get x squared plus 7x plus 10, and we have to factor it. That factors as x plus 2, x plus 5. Now, don't forget, though, they told us one of the zeros. And the direction says completely factor. It doesn't say find the other zeros. Okay, you got to really read these things carefully because there's lots of different ways they can sort of ask you the same question, right? They're asking not for the zeros. They're asking you to write this in factored form, completely factor. So you should write f of x equals x plus 2, x plus 5. Don't forget this one. If x equals 4 was a solution, then, or a 0, then x minus 4 has to be in your factored form. Okay? Because remember, you're trying to get this back, and you have to multiply to get that back. So if you just put x plus 2 and x plus 5, that's just going to get you this one. You need the whole thing. That make sense? The remainder theorem. The remainder theorem basically says that when you do synthetic division, whatever your remainder is actually the solution to plugging in what you divided by for x. In other words, if you were going to make like a chart like this and plug some x in, and you would get some y out, right? If it was a big, long polynomial like this, and you plug in some x, you're going to plug it into everywhere there's an x, and you're going to get some number, some value as your f of c, your y. Well, with synthetic division, that value is the remainder. The remainder will be the solution as if you plugged in x everywhere. So sometimes it's a little easier rather than taking -1 and plugging it in everywhere, which wouldn't be too hard actually, but sometimes it's a little more difficult than -1, right? Doing synthetic division can help you to do that maybe a little bit faster. So let's do this one. C is -2. So again, you're not changing the sign because they're telling you that C is -2. So -2 is going to go on the outside. What do I have to be careful of here? Placeholders, right. There's no x to the third term. So I have to put a 0. And then a 2. And then a -8. And then an 11. Okay, don't forget that 0. Those placeholders are important. So, bring down the -3. Multiply. -2 times 6. So, with the remainder theorem, it's that last number that we care about, right? If f of x is this polynomial and we want to plug in -2, f of -2 would end up to be -13 if we plugged it all the way in. So an application of that then, the number of tickets sold during the high school football season can be modeled by this polynomial, because we know that's really what most of us do in our lives. We make polynomials for situations like this. X to the third minus 12x squared plus 48x plus 74, where x is the number of games played. Find the number of tickets sold during the 12th game. Well, ordinarily we would just take 12 and we would plug it in for x, right? I mean, that's the way you would normally solve this problem. And you could still do it that way. But if we want to use synthetic substitution, we're just looking to do the substitution and then, do the division and then find the remainder. And that's it. So we're going to take the 12 on the outside, and we're just going to say 1, -12, 48, 74. And whatever comes in this box is the number of tickets sold for the 12th game. Why don't you do that one, and we'll just check. Okay, did you get that? 650? 650 tickets sold the 12th game. So that remainder just gives you your substituted answer. That's called synthetic substitution. It's the same thing as synthetic division, but you're just looking at the remainder. Okay, that's the remainder theorem. Okay, the factor theorem. The factor theorem basically says, and you kind of know this already, right? The factor theorem basically says that if x minus c is a factor of the polynomial you're dividing, then your remainder is going to be 0, and vice versa, right? If the remainder is 0, then you found a factor. That's basically what the factor theorem says. Okay. So this says use the factor theorem to determine if the binomials below are factors of f of x. So they're just wanting us to test if they're factors. It doesn't say, find the zeros. It just says test to see if these are factors. Then it says use the binomials that you came out, yes, they are factors. Then use those to write in factored form. So we're really back to where we were before, where we're writing it in factored form, but they want us to test all of these factors first, right? So synthetic division basically twice just to check, is this a factor, is this a factor? And then if you found a factor, then factor from there. Okay, so when we're testing x minus 1, we put a positive 1 on the outside, and this is what we should end up with. So I got a 48 as a remainder. Is x minus 1 a factor? No. So if you get no, if you get a remainder, then no, it's not a factor. That's basically what we're using the factor theorem for here. To test x plus 3, I'm going to put a -3 on the outside, and I'm going to do the same thing. Okay, so this one came out to a remainder of 0, so is x plus 3 a factor? Yes. Since it's a factor, I can take what's left here and factor it some more. I've got 4x to the third plus 9x squared minus 2x plus 1 left, and x plus 3 was the factor. Okay. Now, when I'm left with that not a quadratic, it has 4 terms, right? How do I factor that some more? What would be the first thing you would think to do? Yeah. Yeah, split method or factor by grouping. So that's what I tried here. I tried factor by grouping, and guess what? It didn't work. Not factorable by grouping. It's just not. It doesn't work out. So it's not factorable by grouping. So then what do? That's the big question, right? So at this point, you can leave it. Factored form, you're just going to leave that whole thing there. Okay, 4x to the third plus 9x squared minus 2x plus 1, you can leave it. Next lesson, right, we're going to keep going with this. We're going to do synthetic division again, or, you know, whatever it takes to get it totally factored down, even if it's their irrational or complex or whatever, right? So we're gonna keep going. At this point, you can leave it, okay? So I would like you to try number 7, because that one works out a little better. Okay, so did these turn out to be factors? Whoops, I'm yellow now. Both of these turn out to be factors, right? We tested -4, we tested +5. They both turn out to be factors. When you test -4, you end up with, and when you test +5, you end up with this. They both have a remainder of 0, so they are both factors. Now, we have to write factored form. Well, we know we have 2 of the factors here, so f of x equals x plus 4, x plus 5. We know those are 2 of the factors. Oops, x minus 5, sorry. Those are the 2 factors they gave us. So now we have to find what's left here, right? So which one do we use? Well, you can use either one, but expect that whatever one you use, when you factor it, the one you didn't use will probably be one of the factors, or could be one of the factors, right? So if I use this one, I have 2x squared plus 9x plus 4. And I want to factor that. I end up factoring it as x plus 4 and 2x plus 1. Right? That's how that factors. Well, notice that I'm testing the 5, but the x plus 4 comes out as one of the factors. So that one's already represented, right? We already knew that was a factor, so the only thing we really have to add on here is the 2x plus 1. Because I'm looking for it to be a degree of 3. So x, x, and 2x will give me a 2x to the third degree of 3. Okay, just for the record, we're doing 2, 7, and 11 in class, and the textbook numbers for homework. Scratch that, 2, 7, and 12. So just for the record, right, for number 2, you should have come out with your solution was 3t squared plus 2t plus 9 plus, and your remainder was, 31 over t minus 4. For number 7, the remainder was 0, so f of 3 is just 0. And for number 12, I'm not sure if you got to number 12, but that one should have been factored form x minus 2, 3x plus 4, and x minus 3. Okay, so your homework is to do that textbook pages bottom of the notes, okay?